Well, hello, everybody. I'm Jay again. And this time, rather than introducing the speaker, I thought I would go ahead and talk to you myself about a topic that uh, really intrigued me beginning a few years ago. And the best way I have of describing it is it's the big problem with little c. And so, what is C? Well, everybody in our world, everybody in telecommunications knows exactly what C is, or at least they think they do. But I want to talk mainly about why is there a problem and share with you how I learned about it. To begin with, what is C? All of you know this number probably as well as anybody in the world, but uh, the general convention is that we refer to the speed of light as approximately 300,000 meters per second. This is the exact number. Um, the way this number was derived deserves a little bit of study, because is that really the speed of light? And that leads us to the nature of the problem. The one-way speed of light has never, ever been measured. And many physicists theorize that it can never be measured. Now, you all are probably very familiar with the Michelson-Morley experiments. Began in the late 1800s, and I believe Michelson continued refining his numbers up through the end of his working profession in the 1920s, late 1920s. And from actually 100 years before Michelson-Morley, that 300,000 meters per second number was pretty well accepted. And what Michelson and Morley were doing wasn't so much measuring the speed of light as they were trying to determine the effect on the speed of light by this thing called luminiferous ether, a theory at the time that light waves, or whatever they thought they were, probably not even wave theory at that time, that light needed some medium to travel through, and ether was what they thought it was. So Michelson and Morley were just simply trying to learn more about the ether. What they did as a result was accurately, very, very accurately measure the speed of light. But the only way they could do it was by measuring round trip speed of light and making the assumption that light going from point A to point B was exactly the same speed as light going from point B to point A. A tremendous advancement in the knowledge of the universe came about as a result of their work. But a huge gap in our knowledge, huge gap in the knowledge of physics, results from the fact that from the beginning of time through now, nobody has been able to conceive of a method of measuring the one-way speed of light. So how did I even learn about this as being a problem? Well, many of you were with me a few years ago at a SARA conference when Nobel laureate Dr. John Mather was giving a talk over in the Science Center auditorium on the cosmic microwave background radiation studies that he did that led to his Nobel Prize in physics. At the end of his talk, he invited questions from the audience, and a high school STEM student asked a direct question. And the question was, what experiment measured the one-way speed of light in interstellar space? And without such an experiment, how can science positively refute the thesis that the age of the entire universe is 6,000 years. Now, these are not flat Earth people. These are people who believe that physics does not dispute the age of the universe as being very, very young. This particular student, I talked with him in the cafeteria later, homeschooled, brilliant kid, did his research, and he was of the mindset that without an accurate measurement of the one-way speed of light, any of us could postulate any age of the universe we came up with, and there would not be data that could disprove that hypothesis. I thought about that for quite a while, and I think the student really had a point. I noticed that a lot of people were shaking their head during the questioning, but I didn't, because I think it's a question worth researching. When we assume that the one-way speed of light in interstellar space equals two-way speed of light measured in a near-Earth vacuum, we've made quite an assumption. It's convenient, but is that a valid scientific conclusion? And I believe it is not. But even if you believe that, yes, that's an okay thing to do, that assumption, to what extent can you be certain? And I noticed Dr. Cromarty yesterday had a question very similar to this. How can we know that we are not wrong? And there's nothing more central to our understanding of this entire universe and our understanding of the way radio systems work than a thorough grasp of what C is and how reliable those numbers are. Now, we all know that light can be slower than C. Happens all the time in radio astronomy, particularly the pulsar people are constantly dealing with dispersion measure. Telecom industry, which I came from, we're constantly focused on velocity factor in cables and fiber. And just as a very quick aside, if Rich and I were stockbrokers, we were competitors. And we had offices somewhere out on Long Island, and we were buying and selling stocks at Wall Street. And I had bought my service from a direct cable going to Wall Street, but I had a velocity factor of 0.65, and Rich had spent a little extra money, and he had bought a velocity factor of 0.72. And we're both trying to do an emergency sale of a stock that is going to tank 1 second from now. Rich would make the sale. I would not, simply because of that nanosecond or 5 nanoseconds difference in the transmission of his order to Wall Street as compared to mine. That is multiplied nationwide. This is something telecom companies work with all the time, is the speed of light, speed of electrons going down cables. We see the same thing in deep space. So we know light and electromagnetic waves can go slower than C. But again, what is C? Until 1983, C was a measured speed. That's what Michelson and Morley did. Lots of people worked later, added some more decimal points onto that reading. It was a measured speed. We knew from the time of Einstein that C was a constant, but our goal was to find out what that number was. But in 1983, everything changed. The International Committee on Standards, the people who issue the SI systems of weights and measures, defined C as a set number. No longer is C measured, and the implications of a defined value for a universal constant, as opposed to further trying to find it, is that if we make future measurements that show that C is something different than that long number that's approximately 300,000 meters a second, but the exact number, if we measure it as anything else, C does not change. It stays that same number. What does change is our measurement of time or our measurement of distance. By definition, that is what happens. Those of you who are physicists probably know this already, but immediately we have now taken the International System of Weights and Measures, and we're following what Max Planck proposed. It's generally referred to as Planck Time, but it refers to time, or space-time more accurately, as being the flexible component in these equations. And our measurements would remain exactly the same, whether we're at the center of a black hole, or we are here, or we're on Jupiter. Unaffected by gravity, unaffected by anything else. Everything changes in relation, it's a relativity argument. Everything changes in relation to everything else. But our definition of a second will change, or our definition of a meter will change, but C itself will remain that constant number. So here's the essence of the problem. By not knowing with absolute certainty the one-way speed of light in deep space, we cannot know with certainty the true size and age of the universe or true distances in space. I think that's a pretty profound challenge to anybody involved in the sciences, is to think through this problem. So I have a modest proposal. Let's reset our thinking about C. Let's start a global scientific effort to do the best we can to devise an experiment to actually measure one-way speed of light in deep space. That's a big challenge, probably the biggest challenge ever proposed in the world of science. But if it can be done, let's put the best minds in the world to it. So my challenge to SARA, to all of you here, is think about this over the next year and try to explore some theoretical and practical aspects of the problem, and let's talk about it next year. I have some suggestions as to things that might be done, approaches that might be taken, but I don't want to contaminate your thinking by sharing those. I would like to really get this question out in the minds of good, solid thinking physicists, citizen scientists, anybody who may come up with a concept of how we might do something. And just as an example of something that someone might come up with, we're talking about speed in interstellar space. Well, we now have 2 spacecraft that are just about there, Voyager 1 and Voyager 2. Are there instruments still functioning aboard those spacecraft that can be used in some way to start to solve this problem? If not, can we build something? Can we do a thought experiment of something that perhaps 100 years from now can be built? Even if it can't be built now, maybe we can conceive of it. And as long as I'm proposing wild things, let's call it the Reber device. That's it. Questions? Complaints?
Maybe a comment.
Yes.
I think you mentioned that the students who brought up the argument said, okay, maybe if the speed of light is different in different directions, the age of the universe would be completely different, like 6,000 years. Now, the point is that the age of the universe, and I happen to have heard a talk on that just 2 weeks ago. It was a talk called The Five Pillars of the Big Bang. It's not only the measurement of the cosmic microwave background that supports that. I don't remember all the five. Cosmic microwave background was one. Second one was the fact that there are three neutrinos, something I didn't know. But the age of the universe would be completely different if we only had two neutrinos, which we don't have because we have three. And if there would be a fourth neutrino ever found, that would blow up the Big Bang theory. So this is a strong argument. Another one was the distribution of the elements, which also supports this 13 billion years. So there's some more completely independent evidence for this age. The other comment that I would have, how would a photon know whether it's going backward or forward? Because then you would have to define what is backward and forward, which would mean, as a consequence, that space is not isotropic. And that is very, let's say, a strange thing to think about, that there are specific defined directions which have a different property as far as propagation is concerned than other directions. We never had any evidence that there was something deviating from the isotropic behavior of space. And I guess there's something I'm not sure about. We all know that you can, if you have an antenna, the transmitting characteristics are exactly the same as the receiving characteristics. So you can turn it around just to turn the equation around. I'm not sure though whether that is a proof of the independence of speed of light from the direction. But I would think that that could be an argument. Okay, these are my comments.
Thanks.
I was going to say that one of the foundations of general relativity is the location of the observer is position independent. So that's one. But if you wanted an experiment, an option might be that can be done today is examination of light echoes in the remains of a supernova. Do you see, if the light echo, if the debris field is spherical, then all sides of previous ejections, when they get a flash from the center, would all be have the same depth of where they're going to start lighting up, as opposed to if there was a difference in the speed of light in any position or any direction, then you should see a delay in where the echo is occurring. Now, of course, you have to go through and factor in, at least theoretically, you've got a difference in the distances there, time distances, light seconds, light minutes, light hours, what have you. But that might be an experiment that could be done today with information that is currently available.